Hello everyone, my name is Gabriel Klinger,
And I'm Ruby Peterman.
and today we'll be talking about constructing and analyzing an electric guitar pickup.
We hope you enjoy.
First things first, what are guitar pickups? Pickups are a fundamental guitar component that converts the vibrations of the guitar strings into electrical signals that are then sent to an amplifier and exit as sound. Guitar pickups are constructed from magnets and wire coils in the configuration shown in the image above. The magnets generate a magnetic field around the strings. As you can see in the GIFs to the right, when the guitar strings are plucked, the strings vibrate. Because guitar strings are typically made of metal, they interact and change the magnetic field around them as they vibrate. The change in magnetic field induced by the vibrating metal strings, particularly within the proximity of the guitar's pickup's magnets, results in the generation of an electric voltage, the EMF, in the coil of wire. This electric voltage represents the audio signal that faithfully mirrors the vibrations of the plucked strings, ultimately producing the distinctive tones and sounds of an electric guitar. Therefore, given the physics behind how a pickup works, we know that vibrating a magnetic material, even just a magnet, up and down the pickup will induce a voltage as it changes the magnetic flux in the coil. Of course, the frequency at which you do this will result in different output voltages. But how can we measure this reliably in a lab setup? I'll give you a little spoiler. We use an inductor. So here's a picture of our little setup. We first connect the guitar pickup output to the oscilloscope measuring probes. The pickup that we used was a Musically 50mm single coil Squire pickup that we bought from Amazon. Then we connect an AC voltage source to an inductor, in this case a 50 millihenry inductor. When connected in a circuit, inductors generate a magnetic field. Since we're giving it an AC voltage, this inductor will induce a magnetic flux in the coil, no pun intended. We then also connect a measuring probe to measure the input AC voltage signal that is shown in green. As you can see, once we hold the inductor on top of the pickup, we get this output signal shown in yellow. And putting everything together, here's a wonderful demonstration by Ruby. As you can see, when she holds the inductor over the pickup, we see changes in our response.
To make a Bode plot of our pickup's behavior, we use this equation to find the log magnitude of the voltage out over the voltage in over varying frequencies. We use frequencies of 2 kHz to 100 kHz. This is a resulting Bode plot. It creates a high-pass filter with resonant peak at 10 kHz. The resonant peak magnitude is approximately negative 25.68 decibels with a steady-state magnitude of negative 35.494 decibels. For our original circuit, we did not yet have a physical pickup to model. Because of this, we found values online and set up a circuit corresponding to a common Stratocaster pickup. This first circuit was a low-pass filter with a much higher resonant frequency. However, once we were able to get access to our Squire pickup, we found that we were actually looking to create a very different signal. Using the corner frequency we calculated from the Squire pickup, we were able to find L, R, and C values for the circuit. We then simulated this circuit using software and discovered that the gain on our output was not quite what we wanted. So, we calculated resistor values for a voltage divider to fix the gain. The simulations indicated that our circuit was consistent with the Squire pickup. Here is a picture of our circuit layout. The R1 and R2 values correspond to the gain, and the capacitor, inductor, and R3 values on the right create the filter. To build this, we used two 1 kiloohm resistors, one 10 kiloohm resistor, a 47 kiloohm resistor, a 470 kiloohm resistor, a 4.7 nanofarad capacitor, and a 50 millihenry inductor. We then built our circuit with a breadboard and wires using this configuration. To measure our circuit, we connected the voltage in wires and ground to an oscilloscope's wave generator function, as well as the output wires to the oscilloscope probes. We then used the wave generator function on the oscilloscope to power the circuit with a 5-volt sinusoid. We used the probe to view the output and input optionally of the circuit and varied the frequency of the input signal. We again used this equation to find the log magnitude of our results. Here is a Bode plot for our resulting values. The peak magnitude for the RLC circuit is negative 26.702 decibels, and the magnitude at high steady-state values for the frequencies of the RLC circuit was negative 34.399 decibels. The resonant peak is at 10 kHz here as well. Overall, the behavior of our final circuit is consistent with the Squire pickup, and the frequency responses match fairly well. Given the approximately 1 decibel difference between the two responses, our hardware circuit is within about 5% of the Squire pickup values. This error is likely due to manufacturing errors in our components. Thank you for watching. We hope you enjoyed.